Okay, so now let's talk about the ideal gas. Okay, so specifically, what's the equation of state for very rarefied gases? So this universality of all the gases in that limit was actually already observed and acknowledged and investigated for a very long time, since the 17th century to the 19th century, and there were several contributions that kind of built up this equation. So we are going to see that. And first, we're going to start with Robert Boyle, and Edme Mariotte. So Boyle-Mariotte law. Some people call it only Mariotte law. You know, the naming of these things is always very controversial. The point is that Boyle, and independently, and a little bit later Mariotte, they were considering these gases in this very rarefied limit, and Boyle found that the pressure and times the volume of a rarefied gas was constant. Okay, so if you just plot pressure as a function of volume, then you get an equilateral hyperbola like this. Okay, so what Mariotte independently arrived to the same result, but actually Mariotte was a little bit further, and he realized that actually this equilateral hyperbole that you get depend on temperature. So if you have different temperature, then you get a different set of points along a curve like this. Okay, so yeah, that's the first point. Second interesting observation was by Joseph Louis Gay-Lussac. So there are several things in physics and chemistry that carry the name of Gay-Lussac, and they may be confused with one another. What I'm calling here Gay-Lussac's law is this observation that when you have a gas at constant volume, the pressure is directly proportional to the temperature. So you can say this. Okay, well, this is a different K, right? So call it K prime. So actually Gay-Lussac was building a thermometer, a gas thermometer at constant volume, made with air at very low pressure and temperature, and very low pressure and very low density. And he realized that the pressure was just directly proportional to the temperature measured in the Kelvin scale. So Gay-Lussac, actually, when he wrote a paper about his findings, he acknowledged for his discovery Jacques Charles. Jacques Charles just happened to have found this and also another relationship, which is the one that carries the name of Charles' law, but he didn't publish his paper, his results. And for some reason, Gay-Lussac actually could read it, and Gay-Lussac acknowledged Charles for Gay-Lussac's law. But nowadays we know it as Gay-Lussac's law, and Charles' law we know it as this one. So Charles found that when you have a very rarefied gas at constant pressure, you can see that the volume it occupies depends on temperature linearly. Okay, so this is Charles's law. And then we have one final observation that involves this other variable of state, not just volume, temperature, and pressure. If there were only these three, we already have three relationships. We could build an equation of state with that. But actually we know that the mass is also playing a role. And this takes us to Amedeo Avogadro. Okay, Avogadro. So Amedeo Avogadro, he said that he found that the volume that the gas occupies at any given pressure and temperature fixed, okay, so it could be standard values or something, is not proportional to the mass, but it's actually, well, it is proportional to the mass, but it's actually more than that. It's proportional to the mass divided by the molecular weight. Okay, and at that time it was also tricky to define the molecular weight because people didn't know about molecules. Okay, so they had no idea what the molecular weight was. But doing chemistry, they found that there were these special ratios of masses that did the same thing that the volumes of the different substances that combine in a chemical reaction, and that's how they could assign a value of mass that you have to use to normalize the mass of certain thing that you use in a chemical reaction. Okay, so they found that if you take certain amount of mass of I don't know, hydrogen and oxygen, you can make so like water. Okay, so if you look at the volumes, well, when you have 2 volumes of hydrogen and 1 volume of oxygen, you get 1 volume of water. But when you look at the masses, this nice relationship of 1 to 1 is not maintained when you look at ratios of masses. And if you take the mass of the substance that you're putting in the chemical reaction and divide it by this magical number, this molecular weight, then you find the same nice 2-1-2, 2-1-1 relationship that you have with the volume. But anyway, whatever it is, molecular weight, we know nowadays what it is. Back in the day, it wasn't known. And this is what we call the number of moles, N, okay, number of moles. And moles, we have a unit for it, which is mole in the international system, okay? But this you all also know. So putting together all of these 4 observations, then we arrive to finally the equation of state for an ideal gas. PV, well, actually just proportional for the moment. We don't know the proportionality constant, the number of moles, and T. Okay, and to get the proportionality constant, one thing you can do is to take a bunch of gases and plot PV divided by T as a function of P, okay, for several gases. And this is what is called the Amagat curves. So you can do 2 things. You can fix temperature and take different gases, or you can take one gas at different temperatures, and the kind of curves, which are called Amagat's curves. I forget the name of Amagat at the moment, I don't remember. So these Amagat curves are usually of the similar shape. So imagine that I want to make it right, so imagine something like this. So you take, I don't know, hydrogen. And for hydrogen at certain fixed temperature, you change, say, the pressure, and you look at what the volume is in your system, and you get experimental data like this, okay? And then you switch and you take another gas, I don't know, oxygen or whatever it is, and maybe you find something different. Maybe you find something more like this. So your experimental data are along this line. And if you take another different gas, you may even find something like this. And these are your experimental data. And the point is that if you make a fit to your data, and then you extrapolate the data, you see that they all cut at the same point in the axis, in the vertical axis. And this point is just a value that you can calculate. And this is 8,314.9, or, I mean, yeah, I don't know if this is the most up-to-date value, joule per kilomole and Kelvin. Okay, so that's the ideal gas constant, okay, that you also know. And we call it R, and it's because you see it's really a universal value. So all the gases at very low pressures tend to the same type of behavior. And this magical number is the ideal gas constant, okay? Good, so that's the equation of state of the ideal gas. And now a consequence of the fact that you have such an equation of state. So before we said that the thermodynamic coordinates, if you like, which are relevant for these expansive systems are volume, pressure, temperature, but we know they are linked with one another through the equation of state. So if I give you pressure and volume, you can tell me at known mass of gas, or maybe per unit per mole, you can tell me what the temperature is. And if I give you the temperature and the pressure, you can give me the volume and so on. So it's really up to you to choose which variables you are going to consider independent in any given thermodynamic problem. Okay, so that's what you are interested in. And we are going to see later how making different choices actually gives us interesting relationships that we can exploit. One common choice is the volume and the pressure. Okay, so let's just take volume and pressure. let's put the volume in the x-axis and the pressure in the y-axis. And if I specify a point in this space, well, that point is one state of equilibrium of my system. And if I specify another point elsewhere, well, that's another equilibrium state of my system. Okay? So that fully specifies an equilibrium state, because I know the number of moles that I have, and I can get out the temperature if my system is an ideal gas. Okay, in general, I may not have this relationship, but I will certainly have some sort of, maybe more complicated, sorry, this is not what I wanted to do, T, V, and P, some potentially more complicated expression, but it will certainly allow me to calculate, say, temperature if I give you pressure and volume. So this kind of representation, we're going to call it the VP, or, well, actually written like this, the VP diagram or representation or space. So we can give different names to it, but VP is what just tells you what the X and what the Y-axis are. There are others, right? So you can walk in the temperature pressure representation, and later on we can see that you can use other thermodynamic properties of the system as coordinates to describe equilibrium states, also equivalently. And okay, so far we're just going to deal with volume and pressure.